So let's now start the exercises. Let's start with number 2, where we have to use Euler's theorem to confirm that for any non-negative integer n, 51 divides this number 10 to the power 32n plus 9 minus 7. Now the very first thing we note in the solution is that 51 and 10 are relatively prime. The only prime divisors of 10 are 2 and 5 and none of them divides 51. That's why. Now next we calculate the phi value of 51. The factorization of 51 is 3 times 17. It's the prime factorization. So the phi value is 51 times these two factors. Factors means these two terms. 1 minus 1 over 3 and 1 minus 1 over 17. And then a straightforward calculation shows that it is just 32. Not that we have 32 here. So everything is matching. Everything has fallen in place and it's going to be absolutely straightforward. So by Euler's theorem, 10 to the power 32, which is 10 to the power 5 of 51, is congruent to 1 modulo 51. Note that we need this condition to be able to apply Euler's theorem. So now we consider this power of 10 which is given in the question and decompose it like this using the rules of exponents. Now here congruence I have written means the modulus is 51, that's understood. We are going to finally write it. But assuming that the modulus is 51, you can replace this by 1 because the 32nd power of 10 is congruent to 1 times we have also written it slightly differently like this. The fourth power of 100 times 10 which equals 10 to the power 9 because here we will get 10 squared to the power 4, 2 times 4 plus 1 is 9. Now it turns out that 102 is divisible by 51. So 100 is congruent to minus 2 modulo 51 and then raise both sides to the fourth power. Then this fourth power becomes congruent to minus 2 to the power 4 mod 51 and then multiply both sides by 10. So that's how you get this congruence. And then you calculate it, you find it's 160, which turns out to be congruent to 7 modulo 51. So this power of 10 is congruent to 7 mod 51, which just means that 51 divides this minus 7. That's what we wanted to show, right? So you write the last line yourself. Here the solution ends. Next, let us see number 4, where it's given that an integer a and a minus 1 are both relatively prime to n. And in the context of this problem, it's understood that n is a positive integer. If so, then we have to show that this congruence is true, where on the left hand side we have this sum of powers of a, where the sum starts with 1 and then gradually goes to higher and higher powers and it ends with this one, a to the power 5 of n minus 1. We have to show that this is congruent to 0 modulo n, or in other words, n divides the left hand side. In the solution, we immediately apply Euler's theorem because we are given that a and n are relatively prime. So Euler's theorem gives us this divisibility relation. A to the power 5 of n is congruent to 1 modulo n, which in other words means that n divides this difference. But this difference can be factorized like this, which is a well-known identity from school algebra. And here you can see that this factor is nothing but this left hand side of this congruence and the other factor is a minus 1. Now n divides this difference means n divides this product, but it's also given that n is relatively prime to this. So that means from properties of divisibility, n then has to divide this factor. And when you express this as a congruence, it means that this thing is congruent to 0 modulo n. So that's what gives you the solution. Next we have exercise 6, which is a bit long. The question itself is a bit long. It's an alternate proof of Euler's theorem, another one. So we have been asked to fill in any missing detail in the proof. So let's see what it is. Let P be a prime divisor of n and let GCD of A and P be 1. Because we are talking about Euler's theorem, we need to understand that here we have those things, A and n. Okay, n is the modulus and a is some integer relatively prime to n. Our aim is to prove, or rather the aim of this proof is to show that a to the power phi of n is congruent to 1 modulo n. Okay, so let us try to understand what is written here as a proof of Euler's theorem, an alternative. So it is given that GCD of a and n is 1. That's the hypothesis. Now if p is a prime divisor of n, then GCD of a and p would also be 1, obviously. Okay, and that is why we can apply Fermat's theorem with p as the modulus and we get this congruence. Till this it's okay, we understand what is given. So that the number a to the power p minus 1 will be of this form 1 plus tp for some integer t. For some t means some integer t. Now next what we do, we consider this power of a to the power p times p minus 1. Because a to the power p minus 1 is 1 plus tp, so this becomes the pth power of 1 plus tp. And then we apply the binomial theorem to expand this power. 1 plus pc1 times tp and so on, you know the usual stuff. And the final term is tp to the power p. So here you can see that all the terms have p square in them. For example, here you already have a p and along with that this one is another p. So like that you can yourself verify that all the terms will have at least p square in them except the first term 1. So if now we consider the modulus p square, all these terms except this first one will be congruent to 0 modulo p square. So that's why modulo p square only 1 survives. So here we can write a congruence that this power of a is congruent to 1 modulo p square. There is other stuff also. Now let me write those things. Then by induction we have this more general congruence, more general than this above one. Here the left hand side is again a power of a, but this time the exponent is a bit more complicated. It is p to the power k minus 1 times p minus 1. The right hand side is still 1 like this one and the modulus is p to the power k. And this above congruence you obtain from this one when k is 2. You can clearly see that. When k is 2, the exponent becomes p times p minus 1 and the modulus is p square. So this is only an assertion, so this we have to prove in the solution because this is a missing detail. But this is of course not all because we have not fully got Euler's theorem, so there's more. Next we have this. We have to raise both sides of this congruence to this power where the exponent is this integer. To obtain this, of course, if you take this power on both sides, phi of n divided by this, then the left hand side will turn into this a to the power phi of n and the right hand side will remain 1 because it's just 1. But note that the modulus is p to the power k. Okay. But then from there somehow it follows that you can also write the modulus n. How? That you have to make clear. There is one more thing. How do you know that this is an integer? Because this is actually a ratio. How do we know that phi of n is divisible by this? Otherwise, raising both sides of this congruence to this power actually makes no sense. So we have to now clarify all these things and write the solution. So we start the solution by writing what we said in the beginning. That since GCD of a and n is 1, so GCD of a and p is also 1 for any prime divisor p of n. And next we are going to prove this general congruence, which is actually the main thing we have to do in this solution. And we are going to do so by induction on k. Now regarding the induction approach, we of course first of all need a basis. For basis, the first value is k. You can take k equal to 1 and you will note that in that case this congruence is nothing but the conclusion of Fermat's theorem, because if you take k equal to 1, the left hand side becomes a to the power p minus 1 and this modulus becomes p. So that case is already with us and the case k equal to 2 is in fact proved in the exercise, in the question. So next we make the induction hypothesis. Assume that the congruence, this congruence is true for some integer k greater than or equal to 2, where this k is arbitrary but fixed. But then what does it mean for this congruence to be true? It means that this power of a, this one, is of this form 1 plus s times that modulus p to the power k for some integer s. And now we go through a calculation similar to what's given in the question, but this time we consider the next thing. The next thing in the sense that here you have k minus 1, they are right at k. Okay, so this will be my induction step. Because of what we have here, that is this thing is 1 plus s times p to the power k. What can you say about this power of a? This power of a is just this to the power p. So you have the pth power of this 1 plus s p to the power k. And then again you do your binomial expansion. Just like in that calculation you got one extra p in all the terms except the first one, here also you are going to get, and that is why this entire sum will be congruent to 1 modulo p to the power k plus 1. Just like there p turned into p square, so here p to the power k turns into p to the power k plus 1. But then you have got the congruence, that means the one we want to prove, but when here you have k in place of k minus 1, or in other words, in place of k here you have k plus 1, same thing. So the congruence, the induction ends here and our congruence has been proved for all positive integers k. So we conclude this part by writing this completes the induction. And then of course, as proposed in the question, we raise both sides of the original congruence to this power to obtain this. We have understood how. But the next question is, why is this an integer? So now we need to address that. And that fact follows from exercise 13 of section 7.2. But I still need to clarify exactly how. And this is the explanation. Actually what this exercise says is this implication. Say n is a positive integer and d is a positive divisor of n. Then phi of d is a divisor of phi of n. If n is divisible by p to the power k, then the phi value of p to the power k will divide phi of n by this exercise. And note that phi of p to the power k is this denominator. So that is why this is an integer. But one thing I forgot to write here is that this congruence makes sense only when p to the power k divides n. So you add that, okay, you don't stop it here. You additionally write if p to the power k divides n. Okay, so now we have got this. But from here, then how do we change this modulus to n? That's the last step. And that comes from the fundamental theorem of arithmetic and elementary properties of the divisibility relation. So we wrote like this: by the fundamental theorem of arithmetic, this fact that if p to the power k divides n, then a to the power phi of n is congruent to 1 mod p to the power k. This fact implies this one, where the modulus is n. But again, exactly how? Now the solution, in fact, the formal solution ends here. But we want to be a little more clear about how this last step comes from this one. In what way has this fundamental theorem of arithmetic been used actually? So let's look at a concrete example. Say this is my n, 72, whose prime factorization is this. That's what we get from fundamental theorem of arithmetic. And for the integer a, I have taken 5, which obviously is relatively prime to 72, because here the primes are not the same. There is no common prime. So what you proved here today, that general congruence, that congruence takes on these two forms depending on which prime you are choosing. If your prime is 2 and that k is 3, say, you can see here what we have written. if p to the power k divides n, 2 cube divides n, then a to the power phi of n, 5 to the power phi of 72 is congruent to 1 modulo 2 cube. So here that k is 3 and p is 2. Similarly, you get this one. Alright. So these are two congruences. I mean, the congruences look same, but the moduli are different. How do we multiply these two? That comes from one of the properties of divisibility. This number divides this minus 1, this number also divides this minus 1, and they are relatively prime. So their product also divides this minus 1. That product is n. So that's how you change the modulus from p to the power k to n. So that's where everything becomes clear.